Let's see, maybe I'll just get started. Can you guys hear me?
Yeah, we can hear you.
Oh, okay. All right. I was going to figure out where the list of people were here. Right, good. So I want to go through that homework first. The homework 13, this thing. So that's not it. Ah, okay. Oh, this is our, all right, wait a minute. It's homework 12, sorry. I put up, homework 13 is a dead link right now, but I put up some papers for this artificial intelligence business. Anyway, so this thing, so this is on the quasi XPCS, X-ray photocorrelation spectroscopy, which is like the dynamic light scattering. The same kind of thing. So in the dynamic light scattering thing, we had so you're getting the signal, the light signal is a function of time oscillating. You're going to do a correlation function of that, and then you're going to fit the correlation function with. So this is the correlation function, and it's going to be reduced by the average fluctuation, the average intensity. Then you get this one plus. So this would be like the baseline one, because you've taken out the average, so it goes to one, and then this is the fluctuation component. It's squared because of fluctuations are plus and minus. So you have to square it to get the decay part of it. So anyway, for whatever reason, this is the function that you get out of that. So you measure this, you get that. And then this gamma is going to be basically the diffusion coefficient, and the diffusion coefficient gives you the hydrodynamic radius. That's kind of the standard. And then this is Q squared because it's diffusion. So it goes the mean squared displacement. So Q squared would be 1 over the mean squared displacement. So the position that you pick up, the intensity, the angle that you pick up defines the size that you're looking at. And that's going to be the mean square size if you're looking at diffusion. So that's the mean squared size would be proportional to KT divided by the diffusion coefficient by the Einstein-Stokes equation, right? So when you define this with 6 pi viscosity RH, so you get the hydrodynamic radius from this thing, from that whole setup. Right, that's the dynamic light scattering. The difference is you use X-rays, so the Q is 1,000 times larger here, so you get a kind of atomic scale diffusion when you use X-rays in this XPCS method. Anyway, it's kind of confusing, but basically it's a series of equations, right? So he has equation 1 and 2 in the Yavet's paper. Right? So equation 1 is the same, so that's G2. It's the same G2 that we had here, divided by B gives us 1 plus that thing. So, and then he defines it as C. So the question is like, why is it C and not G2? Equation 1 and 2. So the reason is that this assumes that the system's the same in time, right? And here he's doing a curing system, so it's actually the dynamics are changing as it cures. So let's take like time 1, time 2, and then so this is the same time, and then this is a time, and then a delta t, and t is the argument here. So it's like how does intensity correlate in time with the self? And here the two things are different. In other words, as it's curing, it changes the dynamics. So you have to kind of look at it a little bit differently. So that's why he has T1, T2. And then when he finally gets to these plots, which I mean, I don't know if he invented this approach or not, but basically it seems like it came out of this paper. But so T2, T1 or T2 are 2 times during the curing process. So the difference between, if you have different, like 20 and 60, I mean, you had 40 seconds of curing for this one, and this is where it cured 40 seconds earlier. Then do they correlate? The plot is it's a plot of this C function, which is G2. So showing that they correlate perfectly when the two times are exactly the same, and that correlation drops as you get away from the midline. Then it goes to zero correlation when you get to a long distance away. And if that correlation follows Q squared, then that decay is going to be, so this is a decay kind of laterally across this line for different, actually this is for different temperatures, and these are for different time, delta T's here. So anyway, you'll get a different decay gamma for that, and that'll give you different diffusion coefficient if it's diffusion, if that decays with, if gamma goes with Q squared. If gamma goes with Q to the 1, then it's ballistic, then you get a velocity, which is the case here. So that's kind of what's going on in this thing. So that's why those equations are different. That's what the 2D plots are, the time difference. And then equation 3. So equation 3 is similar to the same equation for the DLS. Equation 3. So this is like just like the same equation here. This G2B and this thing. So it's 2 because this thing's squared here. So you get 2 gamma, whatever, tau. So the difference is he's got the scaled exponential. This thing's raised to some power. And they both have this C and B terms. Right. So C and beta. So the gamma, so basically the gamma tells you if it's a, I think he says what the gamma means here. I think it's got to do if the system's like kind of stuck or not, right? So that basically it's the breadth of this. Is this a real exponential decay, or is it kind of sharper or broader? Right. So he can measure that by putting in the scaling coefficient. So normally this beta would be so beta. So this C should be 1. C is the only C is the only one that you know. So this is capital G, divide capital G by B, and then that C should be 1. So C is the only value of these, and gamma should be 1 also if it's a normal exponential decay. So C should be 1, gamma should be 1, beta you don't really have any idea, but he says beta's a reasonable value for whatever reason. So beta's kind of this where it says function of, there's always a prefactor there. So it's kind of the amount that it decays. So anyway, beta's kind of free for all. C should be 1, gamma should be 1. So his gammas and C's aren't 1. He shows those someplace in the supplemental, I think. I think it's in the question. C should be 1, gamma should be 1, beta, his term, and then figures S3 and S4. So do I have those here? No, this is Triggs. Is there, yeah, that's supplemental. So S3, S4 show his beta. So as with curing, beta changes a little bit. So this is a curing cycle at 1Q and at 1Q, right? And then as stuff ages, so beta changes a little bit. So beta seems to indicate something about the aging process. And gamma isn't 1, right? Gamma's got this higher power. It means it's a more rapid exponential decay. And it fluctuates a little bit with the curing. It seems to have something to do with the temperature too. Right? So anyway, I don't think he talks more about it than that, than just saying that. And then, so that's B. I thought these were pretty simple questions, but it turns out like talking about them, it seems like they aren't. But anyway, figure 3 shows the behavior of gamma. So gamma should follow Q squared if it was diffusion, right? But he finds gamma versus Q is linear. That means that it's actually not diffusion. It's just velocity. So it's velocity because it's only going in one direction. It's only going in one direction because the thing's constrained. So in other words, you're curing epoxy with these giant filler particles. And during the time, they're just moving, they're just literally moving across the screen, right? They aren't oscillating with KT, they're just moving. As the thing cures, tensions are built up and it just moves them like left or right. They don't come back, right? So if it's linear, they don't come back to the original place. If it's diffusion, it would move around and then come back to the same place. But this is just going one direction because it's in a network. So it's stuck. Like as the network cures, it pulls the things. They pull at a certain velocity. So this thing's in inverse seconds because it's a velocity instead of a diffusion coefficient, which would be like distance squared per second. So anyway, so he plots that velocity as a function of time. And he finds out that as the temperature goes up, the velocity increases. That's kind of standard because it's a viscous motion. So the viscosity drops, velocity increases. And then when it reaches a cure point, then the velocity slows down. So that's pretty consistent with what you might expect for a velocity, if it's just a directional velocity. So let's see. So it shows behavior gamma. This makes sense for a reactive network. Yes. Why does the slope change with temperature? So the slope changes with temperature because the system's getting, first it increases, the velocity increases. So slope is a velocity. The velocity increases because the viscosity drops with temperature. Once it cures, the viscosity goes through the roof and then this velocity drops again. So that's kind of what's going on there. And then compare that with the other paper, Triggs S5, which is a supplemental for this trig thing. S5 is this thing. So it's basically, this is gamma versus Q squared. So if this is linear, that's diffusion. So the other one was versus Q. This is versus Q. And that means it's a ballistic it's a velocity. It's a directed motion. And this is Q squared. It means it's not directed, it's random. It's a Brownian motion. So any time this is Q squared is an idea that you have. Whenever you see distance squared, it's going to be diffusion. And that's what they get for this. And the reason they get that is this in Yavit, he's using micron-sized particles with X-rays. So all he sees is this kind of jostling of the things as it solidifies. And in this case, they're smaller than the network. The particles are smaller than the network, so they're actually diffusing around within the network. It's higher power, so it means they're I forget the name of it, excessive diffusion. In other words, they're diffusing faster than they should, or at a greater, I'm not sure what that means. Basically, it's a little bit higher than 2, but the data is also spread out a little bit. Anyway, so explain the difference. That's the difference. One's diffusion, one's ballistic velocity. Then Triggs 2020 paper uses his equation 3, Yavit's equation 3, to obtain the complex viscosity, applying the methods of diffusive wave spectroscopy. So this group, the trig group, the trig group. So they do almost the same experiment, but with nanoparticles, and then kind of a more controlled polymer. But then they do this, they get the complex viscosity, which is something that you can get by doing this, by using the particles that they put in as a tracer to measure the viscosity of the matrix. And that's the same thing as when you do that with light, they call that diffusive wave spectroscopy, which is this thing. So basically you put in tracers, put the light in, do the dynamic light scattering measurement on the monodispersed particles that you put in. So you already know RH. So you know what the diffusion coefficient would be, what you don't know. So the gamma is going to be 6 pi times the RH heterodynamic radius, which you know here because they're monodispersed, and then times the viscosity, right? So you can get the viscosity out of this if the viscosity is changing with time, like in a curing system. So that's what they're doing. They're getting the viscosity out, not because they put in monodispersed 12 nanometer particles into this, right? Somewhere they say what particles they use, but 15 nanometer particles. They're fairly monodispersed, so they're narrow distribution anyway. So Right, so from that you can get the viscosity because the signal you're getting is composed of a diffusive, you can say it's a diffusive kind of a diffusive motion. It's going to be viscous, which follows Brownian motion. So it's a combination of these two plus an elastic motion that's constant. It's basically the measurement that you're doing of getting this mean squared displacement, which is gamma, basically. So the gamma in the DLS thing, you're measuring this R squared. So basically, by measuring gamma, you're getting R squared, and R squared is composed of a real and imaginary component. And if you do a Laplace transform, which is a sum of all these exponential decays, then you can iron out this complex, the complex modulus, and omega frequency over the modulus gives you the complex viscosity. So you can get the complex viscosity from this measurement. Right, so it's a little bit mathy, but basically you can get the complex modulus, you can get the exact things. We showed, like for a worm like my cells, you can get the rheology measurement on a machine, and this DWS measurement is the blue lines, and they match up perfectly and give you a higher frequency part of the thing. So anyway, that's what they're doing here. The same thing, except instead of getting complex modulus, they're getting the complex viscosity, which is, again, here they show the frequency. So the complex modulus divided by the frequency gives you complex viscosity, right? So you can get either one here. So anyway, that's what they do. So they, instead of kind of looking at that, like here to see the behavior, they go and take the square of the complex viscosity, gives you the viscosity. So you square the complex. So you take the absolute value, square it, and take the square root, get rid of the complex part, and then you just get the viscosity. And someplace they plot the viscosity they get with this DWS by XPCS thing, which is black circles against the measurement from the viscometer. So they show that there versus the cure time. So they could have done a lot more analysis on this stuff if they wanted to, but basically they just show that to show that it works. Just like there's here, it's kind of shown, it would be like looking at this part of this and saying, oh, it works. But there's a lot more information to get out of that if you wanted to. Anyway, so that's kind of what's going on there. That's what they did different. Paper uses equation 3. Figure 4 of trig shows a comparison of bulk rheology. That's what I just showed you. Describe why it's useful for this system. So it's they don't take advantage of it for the system. So I'm not sure. It's just like a show of force. It isn't this, wherever that is. Where is that thing? Anyway, they're just showing that you can do it in that case, right? So it isn't, oh, it's here. So they're showing that you can do it. They don't actually take advantage of that. So it's kind of a funny thing to show it and not use it, but they do show it. So it is different because of that. Then there's another paper that's almost exactly the same. It came out the next year too, which is this Japanese one, this thing. And then, so the difference, so they do exactly the same thing, use the same equations. They show that C equation somewhere, I think, the C thing. So it's all just copied, right? And then so it's kind of odd. This went in Nature, their thing went into advanced physics. Then the other one was macromolecules. So it's kind of different ranked journals, but basically the difference here is that they frame this up. So they also do monodispersed particles. They also do more controlled curing. They have better graphics. And then they do something, and then they throw in like this is what people do. You kind of dress it up into like something more, like you put in some philosophical thing into it. So basically they're saying like, as it cures, so you're going to have like regions of higher curing, right? So those regions, if you look at the dynamics of this, there's some still like moving around independently. Those regions where it's like making clusters. So they claim that by using this method, they can sort out the fraction that are clustering, the fraction that aren't clustering, and watch that as a function of time as it cures. You tell like maybe the uniformity of the curing under different conditions, like cooling rates and things. that's my read of it. I didn't read through this in depth, actually just skimmed through it, but so they're using the same equations. The other difference is they use NMR. So using NMR, you can also do molecular relaxation time. So they do that, and they break up the molecular relaxation time into 3 parts from an NMR measurement. So we haven't talked about NMR, but basically they throw that into, and they get kind of the same, something that agrees with itself. So it's a little bit different, and it's mostly different in that they throw in this kind of more flashy dynamics thing that people are kind of interested in. This kind of like clustering idea of things. So any questions on that? It's kind of a lot. I mean, there's 3 papers really, but all the same theme, and it all has to do with dynamic light scattering applied to X-rays.
Hey, Dr. Beaucage.
Yeah, yeah.
A lot of the 5th-year chemies have our expo tomorrow. Is there any way we can get an extension on this homework? A lot of us are going to be busy all of today and tomorrow because of that.
All right. Yeah, that's all right. I mean, is it enough to say till Wednesday or something? Or it doesn't matter that much, So it's just the next homework's going to come on. That's the issue.
Yeah.
People turn it in late all the time, So I don't mind.
Okay.
But basically, keep the deadline at least before. It's good that I can grade it before Wednesday too, but otherwise, it probably doesn't matter much, So see, it's okay if you want to do that.
Okay.
But it's just like it's going to pile up, because the next homework, I think this one should be pretty easy, I think, I think the next one's going to be a little bit dicier. Not exactly dicier, but you have anyway, I'll show you what's going on there. But you can, yeah, it doesn't matter. Okay. But it'd be good to have it in as early as possible so I can grade it, and then I can say like how you did on it. So yeah, it's not the job fair. Oh, it's the expo, it's a poster thing.
Yeah, it's for our capstone class.
Oh yeah, I have to go to that. It's downtown, right?
Yeah.
All right. So yeah, it doesn't matter. Just whatever you want, it's okay. But just try it. It'd be good if some people turned it in, then they could grade a few of them. I still haven't finished grading. I mean, the other ones that were turned in late, I haven't graded them yet. So, but. All right. All right. Any other things on this? So, yeah. All right. So I want to go to this. Let's see. I might just go to the web page again. This is a bunch of these. So machine learning, artificial intelligence, there's a bunch of things in here on that. So some of them are kind of neat to look at. There's this recycle center downtown, or it's on Vine Street. They're using, this is like an application. Oops, let me turn this down somehow. Oops, there. So they have a robot, and it learned to pick out the milk jugs. So it just picks out milk jugs from the recycle stream. So this is AI. So they tested this by running it. It didn't get the milk jugs. They like made a data set of that, and they optimized it until it picked just milk jugs out of the stream. So that's like an artificial intelligence driven process, right? So anyway, that's kind of like one application of these things. It's kind of, I don't know if you could see that, but anyway, so and then they also have a kind of semi AI based separation. I show a bunch of the recycling things in here somewhere. But anyway, just clicked it, right? It should be here. Anyway, so that's one thing that they're using. So there's a lot of AI things, right? In fact, the last thing is like a 40-minute video about the Gaza war and how they're using AI to identify targets there. It's like, there's like good and bad to this, like recycling to like finding people to kill or whatever, so it's good and bad to this AI business, right? So there's also a bunch of cases of different applications of AI in Polymer research. So there's just just this whole slew of things. And some of them are like high density polyethylene. Some kind of really simple, basic materials, And then this actually 2 papers on polyolefins in here. But so a lot of it is like saying, yeah, gee whiz, I can do it type paper. Not like it's applicable. This paper they were going to look at so they let's see. This isn't refreshed. That's why. Okay. So this paper they right, so they figured out a way. So you need big data sets to do this. They figured out a way to automatically manufacture black copolymers. So you can make, so they end up making like hundreds of different black copolymers with different, see, I mean, it's an array of like a huge number of black copolymers that they want to use to use to bind with active like these are native state proteins. One of these is glucose oxidase, and then the other ones are other kinds of oxidase. So these oxidize something like glucose and then turns it into like a pH meter. So if you include this on some kind of a strip, and then you can oxidize the glucose and use a pH meter to read like how much glucose is in the system. Right. So, and then you can do that with a variety of different oxidase proteins. Anyway, so the problem with these is if you stick it in the oven, it denatures immediately. So people are looking at binding a black copolymer onto the surface of this to prevent it from degrading. So there's a huge number. So that they use that machine, that black copolymer machine. This is a group at Rutgers. This guy, I think Michael Webb's the guy I heard give a talk on this, but basically they use that machine to produce a slew of polymers with different side groups. So these are acrylate polymers. So you have the acrylic group, then they just put on a different polarity or amine or so anion or cationic or hydroxyl oleophilic type things. Tetraamine, so anyway, so they can stick all those on and then make different molecular weights of polymers using that automated synthesis thing. And then at the same time, then they can test the activity. They make a tray with thousands of polymers and these 3 things. So you get a huge amount of data. That's the point. You get thousands and thousands of data points. And then they can tell like how long does it take to degrade it, basically. So you get a gigantic data set. So the idea of this technique is like huge data sets that you either produce yourself with a machine like this, or you collect from the internet. So that means you have then you got to use that data set to optimize some parameters to make a predictive capability to say which one do you want to synthesize next to make the glucose oxidase last longer. Right, so that's kind of the idea of this scheme. So anyway, so that's the theme of this. So you can tell like this is so it's impacting polymer research. It's impacting kind of everything. This kind of AI thing, AI machine learning. So UC has this business analytics thing. So the idea is so it's a program they have in the business school to do this. So there's a lot of jobs in this area. I think it ends up being a little bit of like a dry topical area in a sense, but so it's a lot of, you can see like it's going to be a lot of data collection, and then it's going to be like feeding that into some kind of software that will do this analysis. So the homework this week is to go through that exact software. This thing, the nice thing is that this guy at Rutgers, first off, it's totally important. Like these kind of drug development things are pretty useful. I mean, it's not like identifying targets, to kill or whatever. So it's like basically actually going to some good cause. But also, let's see, we can get back there. So also he's got so this paper, the second paper here, let's see. So if you go to 13, this one is like a paper to teach you how to do it using his data. and then using Google Colabs, right? So it's pretty sweet. So you can just go to his his data set here, which is this Gourmet Lab. So I guess Gourmet's the guy. Then that'll take you to Google Colabs. So they have a thing going on there. And then you can actually, this is actually Python code that runs. So you can run it just on a web page. So maybe I'll try to go through this on Friday, like how this thing runs and how you do this actual thing. Right. So all the components of a research style artificial intelligent machine learning process is in here. And you can go through it step by step. So what I'm going to do is probably figure out a way to modify this a little bit. So you can go through it step by step, and then afterwards modify it a little bit with change the parameters a little bit. Let's see what happened in the chat. Yes. Okay. All right. So and just get to this. So yeah, this business analytics thing is the same thing. It's just like say you're going to go get the prices on something in the store. So you're going to have like data collection all over the place, or you're going to go to the Internet of Things, means like the internet. You're going to use the internet to gather data. So you need a huge amount of data to do this. So you're either going to get it from the internet, and in this process, you can't have like missing data, and the data has to be all in the same format. So a lot of this stuff is like reformatting data or figuring out programs to fix data so that you get a set of data that's all in the same format of all different sources, right? So, and then the quality of the data matters, things like that. So I think you can figure out what matters here more or less. But so and then you have to take the data and then convert it into something that you can act on, meaning a number from 0 to 1, right? It has to be like a yes, no, or a gradient term. You can feed into some function that's going to predict what you want, like did somebody buy the gas or whatever, right? So basically, there's a lot of like sorting of data. So each of these steps of this thing, collecting the data, has Python code already written through various packages that you can just implement. Like, so you don't necessarily have to write, because this has already been done. So, and everyone's kind of doing the same thing, just on different numbers. Ends up just being like binary answer. Do you want to go this way or that way? Right. So with some process you're doing, or whether you're going to market something. So anything you do, it doesn't matter what it is. It could be like developing the protective block copolymers for the glucose oxidase, or it could be like whether someone's going to buy a meatball sub at the Speedway. Right. The computer doesn't care what it is. Right. So, or it could be like, are you identifying the right guy to kill? So it could be a lot of different things. So there's this kind of benign process, and then there's like how people use it. Right. So it's like anything else, So anyway, so then you're gonna have some kind of model that you apply, or you're just gonna, so a model would be like fitting the data, or you're gonna use machine learning, like there is no model. So you just say, I have all these numbers. I'm going to have a weighting factor for each one of the numbers. I don't know what it is, but initially I'm going to guess it's 1. Then I'm going to let it cook, and I'm going to optimize. I'm going to say, like, can I predict from that using 1? And I'm going to change it to 1/2 and see if it gets better. Just kind of like a trial and error process to get the weighting factors for all the input data to get the output data that you want to get. That's more or less what machine learning means. So it's going to develop its own function by trial and error, basically. Right? So, and then make predictions. And then the predictions can be like, I need more data. So the prediction can be like the result. Yeah, they're going to buy meatball subs on this day at that hour. Or it could be like, I need to know a little bit more information about what kind of meat they like. And then if I fill in that space, then I can feed that back into this, run it over again, and then I can kind of improve the process through an iterative process like that. So if this whole thing runs on its own, it looks like it's thinking. It starts to act like a human brain. Right? So that's kind of what the scheme of this thing is. So, I mean, and you've already interacted with the stuff. Like when you go to when you get on the internet and it reads kind of what you bought or what you're doing, and then it suggests the next thing that you want to buy and puts up the ad, and it's like, geez, how did it know that I knew I wanted that? Right. So that kind of works. I mean, it's kind of scary, but basically that can work. That can be an advantage. It fails, it's like these automatic phone answering things that ask you all the questions, and it seems like it goes nowhere and then dumps you in the wrong place. Right. There's ways it works and ways that it absolutely doesn't work. And it tends to kind of dehumanize the situation. So it's not great in that sense. Anyway, so in terms of like interaction, in terms of science, business people see that it's an advantage because you don't have to pay a pension or anything just to a machine to make decisions. In terms of like films and things, like you can not pay the writers and the actors if you can synthesize fake people that do exactly the same thing as the actor would do and do it perfectly every time. You don't, and they just never age and things like that. So anyway, there is like a kind of negative side to this whole thing, so you have to kind of keep that in mind, I guess. But and then there's these issues of like, if the machine by trial and error comes up with some answers, does that just go to the guy who owns the company, or does that go to the people that put the data in? So if they took the data from the internet, do those people deserve a cut? So who gets the profits from this advancement? It's like robotics, right? It's the same kind of thing. Like if you replace all the line workers at a car plant with robots, then yeah, that's the way you should go. But basically, so they've cut their costs in like 1/8 to make a car, but the car price is the same. So they don't pass it on to the consumers. They don't pass it on to the workers. You just pocket it, right? So this kind of issues about equanimity of the whole thing and that business. Anyway, anyway, this is from this webpage, data analytics, but it's kind of the same thing. So you can take this thing down a path, different paths here. So let me hide this thing. Anyway, so descriptive. So you can do collecting the data, and then you can just describe what happened in the past from this kind of approach. Then you can use that to predict what will happen in the future, like the weather and things like that. And then you can kind of do this predicting like long-term kind of things. That's like a machine learning process. And then if that machine learning is used to tell you what to do, then that's artificial intelligence. Right. So there's kind of different stages of the same thing. Right. So basically there's a gradient of getting into this. Till finally you just say, so in this paper we'll look at they use the data to do predictive and check the existing data with that. And then finally they say, like, we want to predict what kind of block copolymer to make for this specific protein to protect it. Right. And then that's artificial intelligence at that point. Right. So there's just a gradient and how you apply this business. Right. So then you have to consider like what this kind of thing can solve, because it looks like it's so powerful, like ChatGPT can give you any answer, right? But basically that's not true, right? So this thing is only taking what exists and then predicting from what exists, right? So it's only following. If you had never done a measurement on a room temperature superconductor, right, it wouldn't suggest to do that, and it wouldn't come up with like the discovery of room temperature superconductors. Right, this process can't do like new things. Kind of, it can look like it's doing new things, but it's really just assimilating things that already existed. So it's not going to solve like global warming. It's not going to solve the plastics waste problem. It's not going to invent the internet. It's not going to invent block copolymers, but it can use existing block copolymers to make drugs better or to make protein processing better. Right, so you could use it if you have a huge slew of data, like heterogeneous catalysts for polypropylene. Yeah, it could optimize that and predict the next one that would be better. Or if you're making room temperature superconductors from any oxides that exist on Earth, right, multi-oxides that exist on Earth, then it could come up with the best combination of materials. within an existing framework of making room temperature superconductors using oxides. That's not going to say like a block copolymer could do that, right? Which people have done. So basically, there's some problems that can be addressed, some that can't, right? But generally, like in industry, there's not like, unless you come up with a new business, right? Like flying cars or something, then basically most of the problems you deal with are this kind of problem. So for business, this process optimization thing, that fits pretty well with this AI machine learning thing. So in terms of application fields, it's got some advantages. Also, there's also we have national instruments like the synchrotrons and the neutron facilities, and they're getting more and more powerful, and they're being more and more automated, so that you can take, like, for instance, X-ray scattering data. If you set up an array in like 15 minutes, you can run 1,000 samples on it, right? So then you could say, well, instead of just running one sample at a time and figuring out what's going on, forget about figuring out what's going on, just run the 1,000 samples. Then you have 1,000 data sets, each of which is going to produce like 9 numbers. Put those 9 numbers into an array, weight each one, and give the output I want to get. And then say I'm going to adjust that until I get the right mix of weighting factors for each of those numbers to get the output that I observe, and say an output that I desire. Then go back in and say, what should I make from that? Like how could I make the thing I want to make? So there's a bunch of examples on the web page here of that, right? So that's basically what one of them is. One of them is this dielectric paper. So basically, how do you make a capacitor, a polymer capacitor, where you have a ceramic and a polymer? You got to make a supercapacitor of it, so that can replace batteries for short-term storage, right? So in other words, storage on the like 10 minutes storage type thing. And if you say you have solar array and the cloud comes in front of the sun, or there's an eclipse or something, and then you have 10 minutes of darkness, but you need to store, if you could store the power, then you wouldn't have any fluctuation in the grid from that. So these supercapacitors there's a lot of short-term storage issues in the grid, right? So basically, this thing is using that approach to develop the right polymer and the right ceramic that would go together at the right composition to produce the best supercapacitor or something like that, to store short-term storage. And then how is the structure developed? Right. So I kind of use this paper as like a theme in these set of slides. So anyway, so also the reason why people are interested in this is that there's a ton of money in it. So basically, however much money that is, it's like $1 trillion or something. This is billion, so it's $2 trillion, 2022. It's like dumped into this area: machine learning, artificial intelligence, Internet of Things. Right, so this is like get all the numbers, collect them together, have it learn how to do it, and then predict what the outcome's going to be, like 1, 2, 3. Right. So then you can see like every part of the government is involved in this because it's a big pot of money. So everyone's like grabbing for the dollar. So anyway, so how do you do this stuff, right? So how are you going to do this? Well, actually, there's no proprietary software for this, I think, at all, right? So it's all been driven using Python, and then these kind of packages, right? And each of these packages is going to be has its own little world, right? And each does a little bit different. So this is like take the data, however you got it, from this automated synthesis machine or from the internet, and then classification. If you click into this as examples, it'll teach you how to do it. And then there's Python software in here that you can just run on Google Colabs and it'll just do it. These are different kinds of regression. So once you have a way to classify your data and then convert it into numbers, and with weighting factors, and how you're going to regress this thing. So just take, like, say you have 10 numbers from each of 1,000 samples. Each number is going to have a weighting factor. Maybe you just sum them together to get a final target thing that you want. Then say the data sets are here, and then what's a function that fits along this? So just by changing the weighting factors, get it to match up with this, and then basically use that to predict like what's the best one if you want to get the lowest value of this target, say, or the highest value. Right. So different regression processes. So again, like if you click this, it goes into like an extensive array of thing. And then if you have so many data sets, you want to say this type A, type B, type C, there's clustering algorithms. If you have 20 parameters, you want to reduce it to one dimensionality reduction. So you just have an XY plot. How to select what fitting thing to do with this, a linear sum, some power series, whatever, right? And then taking this data before, so classification of the data, then also like how do you process it, right? So all these things are code already written, and you'll see in the example it goes through all of these, right? So he goes through each of these things. So that's just one of these softwares. There's that's the scikit-learn. That's the one he uses in this paper. And then this Keras is a similar thing, but it's for different aspects of it. This is for like images. Like if you say you have a 2D detector for X-rays, like was shown in this week's homework, and then you want to, instead of analyzing the data the way it was done, you want to just take each. So you have 1,000 by 1,000 detector, so you have 1,000,000 data numbers, right, for each image. And then if you take each of those 1,000,000 data numbers, could you just throw that in and not have any understanding at all and come back out with like the velocity of the particles? Like it's possible to do that. That information is in that data. A machine could optimize by machine learning and just come up with the velocity and might do it faster than your analytic technique you're using now, right? So it's basically this kind of image. A lot of times you're ending up with an image, and this Keras thing is a way to deal with images, right? So how do you, so if it's just a photo identification on your phone, is it you or is it someone else? This is the thing, the Python code in here will do that for you. PyTorch is this is the whole machine learning step thing. So basically these are also Google Colab files. We can just click through and let it kind of run the programs that already exist, right? So you just need to kind of figure out the scripting language. Python is basically a scripting language, so it's going to have functions. Just need to know what the function and the arguments are, kind of how this would work. But it's all like linear programming. It's not pull down menu or anything. So basically it's a little bit different than what you're used to. But and then there's this data camp thing will teach you. It's like this is just a teaching. So those are using things, and this is just a teaching thing. So I guess we got to do this. All right, so other. Oh, if I say other, I have to do something else. Email and newsletter. That they're collecting data to use in machine learning when they do that. But anyway, so this has so it goes through, when you get into this, it goes through steps of what you want to get, and then it finally gets you to a point where it'll just be what you want. I think I did that already, going through that somewhere here on the web page. That's what I want. Somewhere in this, I think I have that thing here someplace. Paper. Anyway, it's in here somewhere. There's a link directly to the thing that you want on that. I don't see it right now. Anyway, so data camp's a good thing too. So these are the packages most people are using, right? So they already exist. You don't need to code anything. It's just a scripting process, right? So then let's see. That's good data. Yeah. So Wednesday, no one's going to be here. So maybe I'll just yeah. So we can't do Nichols then. So I'll just probably go through this stuff some more on Wednesday. right? And I'll just record it the same way. So that's probably because there's plenty of stuff to go through here. This is just a picture of those pages from that. So anyway, in polymers, there's an issue of so you end up with these complex molecules. Like block copolymers is a popular item here because you can just change the properties by just changing one of these things. So people made money off figuring out how to, like research money off figuring out how to convert any block copolymer into like a code sequence. It's a linear code because a computer can't read this, but it can read that. Right? So it's like how many carbons, then the terminus of the block. So you just figure out a way to write a code for polymers, right? So basically, if it's random or if it's block, you have to have them like the weight of the sections and things like that, right? So these are MIT people. So this is kind of like money dump to just develop this SMILES program, right? So it's basically kind of taking so in other words, this bio paper is going to be using SMILES to identify their block copolymers so they can feed this into a machine learning code, right? So you need to have this is like step one of the thing, but you can see it's 2021. So it's pretty recent, like what people are doing in this. What's this thing say? So yeah, so each data set, so how you talk about data, that's what this is about. So the preamble, the metadata is like the source, the year, the date, whatever, the temperature, humidity, kind of everything you could say about where the thing came from. And then that has to be in a consistent format for all the data that you have, which you might collect from the internet, right? So, and then some of this might be missing, like it might not say them like the weight of the blocks, things like that. So you have to, the machine learning can actually fill in the gaps. That's one possibility. Or you can dump data that isn't a complete data set from the internet, right? The Internet of Things. So, and then how you classify it into species, and then how that can be, what kind of information you're getting, like the subsets of the information, right? So anyway, this polymer genome is an approach to like trying to do this kind of setting this up in a usable form so that people could access it. So see, they're using the same kind of code, and then you're going to be able to go to this web page, this polymer genome at Duke. So they get a ton of money for this, and then they collect all the data. And if you have an NSF grant, they approach you and say, like, give us your data. They have to feed it into their thing, and then they're going to pile it up so that some kind of roving machine learning thing is going to take that data and be able to predict something from it, right? So again, like who gets the money for the thing that's predicted from it, that seems to be a free for all right now. So anyway, so yeah, maybe on Wednesday I'll start here, like on slide 13, and kind of go through this paper by Zhu, which is also here. Let's see. So this is slide 13. Zhu papers within the brackets here. So it's this thing, Zhu paper. It's basically this developing these dielectric materials. So I'll kind of go through this on Wednesday. This isn't the one we're going to use for the homework, but basically it's good to look at two with different topics, because then you can say like, what is the essence? And you can see like where they're using the same tools, right? Even the same programs to do the predictions, different kinds of data sets. And then how you can, what the similarities are, and maybe you can get a feel for how this thing actually works. I think the only way to get a feel for it, the guy from Rutgers is right. The only way to really get a feel for this stuff is to go through the Google Colabs Python routine that they did with their data. Actually go through a series where they've done this data collection. We can see that getting the data is a big part of this thing. But once you have it, then the procedures are going to be almost the same for everything you do. Then it'll come out with the result on it. So yeah, why don't we end it there for today? Any questions on anything? It's a lot. This is a lot of stuff, but basically, I want you to have a feel for, not to be an expert, to just have a feel for how this works. Yeah, yeah, have a good eclipse day, you guys too.
Wait, are you going to see the eclipse?
Yes,
Are you going out 30 minutes to go see it?
yeah,
Well, I hope you have a good one too, then.
yeah, you too. Okay. All right, I'll see you guys later. See you Wednesday.